This question asks us to determine how much carbon monoxide is left at equilibrium, and we will use grams since we're talking about mass. We are given this reaction equation at equilibrium, and we're told the volume of the vessel and that the equilibrium constant is 4 at the particular temperature this reaction is occurring at. We are also given the initial number of moles of each species before equilibrium is established. Since we want the amount of carbon monoxide present at equilibrium, we can use an ICE table. Some call it a rice table, where R is the reaction with a ratio, in this case 1:1:1:1. I is the initial moles of each species. C is the changed moles, which is the moles of reactants used up and the moles of products formed. And E is the moles left at equilibrium. Now we do not know how many moles of reactants are used up or how many moles of products form at this particular temperature. But we can express their values in terms of X. And since the mole ratio is 1:1:1:1, then if X moles of carbon monoxide are used up, X moles of water are also used up, and X moles of hydrogen will form, and X moles of carbon dioxide will form. Remember, the changed moles must be in the same ratio as the stoichiometric coefficient ratio. To get the equilibrium moles for the reactants, we take the initial moles minus how much was used up. And so we get 0.6 minus X moles of each reactant present at equilibrium. Then, to get the equilibrium moles for the products, we take the initial moles plus how much was formed. And so we get 0.1 plus X moles for each product present at equilibrium. Now these mole values are in terms of X. We need to be able to solve for X so that we can work out an actual mole value for carbon monoxide, and then from this we can work out a mass of carbon monoxide. We can use the equilibrium constant expression to help us solve for X. Remember that an equilibrium constant expression is the concentrations of the products divided by the concentrations of the reactants, with each raised to the power of its stoichiometric coefficient, which is 1 for each in this case. Now we know that the value of Kc is 4, and we need the concentrations of the 4 species for this equation, but we only have the moles of each species in terms of X. However, we know that concentration is equal to number of moles divided by volume. So if we take the number of moles of each species in terms of X and divide by the vessel volume of 2 decimeters cubed, we get the concentration of each species at equilibrium in terms of X. We can now substitute these equilibrium concentrations into the equilibrium constant expression, as well as the value for Kc. The 2's in the denominators will cancel, and we can take the square root of each side, then getting rid of the denominator and multiplying out the bracket. We can solve for X, which is 0.367. Now, since the moles of carbon monoxide at equilibrium is 0.6 minus X, we can substitute in the value of X, and we get 0.233 moles of carbon monoxide present at equilibrium. All that is left to do is to convert this to a mass. We know that number of moles is equal to mass divided by molar mass, and so the mass of carbon monoxide is its moles times its molar mass. Putting in the mole value we just calculated and the molar mass of carbon monoxide, we get 6.52 grams at equilibrium.